before x is equal to 9, for instance, we let x be equal to 4, then we are going to get the y prime of 4 being that. And simplifying further, we are going to get the y prime of 4 being 1 over 4 minus 9 over 16. Now, y prime of 4 is equal to minus 5 over 16, which is less than 0. We also move on to find other values that are greater than 4 for x. For instance, x is equal to 16. With that, substituting, we are going to get that. And simplifying further, we get the y prime of 16 being equal to 1 over 8 minus 9 over 128. Welcome to Numbers Simplified. In this channel, we seek to simplify and solve numerical problems, covering stationary points, max or minimum points. This is part 7, so make sure you subscribe, like, share, so that you don't miss out on any of our future uploads on the differentiation playlist, as well as other playlists. Make sure to check out other playlists that we have covered thus far. Now, in this video, we cover the method of sign change. So this is method part 1. We are going to cover method 2 in other videos. So make sure you subscribe so that you don't miss out on other videos. Now we consider y to be equal to f of x. Now with that, if our f of x is given to be that graph over here, we can see that the gradient of the curve y is equal to f of x is negative from a to p and from q to point b. This implies that the dy dx is less than 0 in these regions. Now, remember from our previous video, part 6, where we covered decreasing functions. So from a to p and q to b, these are decreasing functions in these regions. So that is what we want to recall. Now, moving on, the gradient of the curve y is equal to f of x is positive from p to q. This would imply that the dy dx is greater than 0. Therefore, from p to q, the function is increasing. Now, we take note of something as well. The gradient is 0 at points p, q, and b. This implies that the dy dx is equal to 0 at these particular points, because these points are known as the stationary points or the turning points. So the gradient of any turning point is always 0, or the dy dx of a turning or stationary point is always 0. So a stationary point is called so because it is turning. It is not going anywhere, but it is the turning point. Now, let's look at the types of stationary points that we are going to cover. The first one is the maximum point. So a maximum point occurs when the dy dx is equal to 0. That's the first thing. Then the second thing is the dy dx should be greater than 0 before the maximum point, and the dy dx should be less than 0 after the maximum point. Recall, at the maximum point, the dy dx is equal to 0. But if we get other values that are less than the value, x value to be precise, of the maximum point, we are going to get a dy dx, or the gradient, which is greater than 0. And after that maximum point, we should get the gradient, which is less than 0. Great. So, for instance, point q is a maximum point, for we see that from p to q, the gradient is positive, and at q, it is the maximum point, and q to p, the gradient is negative. So that is what we are saying. That's how we get the maximum point. Great. Let's have a look at an example written in black. Example 1. Find the coordinates of the stationary points on the curve y is equal to 3 plus x times 2 minus x. The solution. So the first thing that we can do here is start by sketching the curve. We know that the curve has got a maximum point. So if you have forgotten or if you haven't come across anything of this nature, I encourage you to check out our video on quadratics. Check out the whole playlist, but specifically the quadratics maximum and minimum graphs. Great. So we have the sketch over here because we know that this one is a maximum graph that has got a maximum point, and the points of intersection with the x-axis are -3 and a +2, like that. Then in this case, we don't know the maximum point as yet because that is what we are trying to find. So now expanding the brackets or the parentheses, y becomes 6 minus x squared. And with that, we find the derivative. dy dx becomes -1 minus 2x. And that is equal to 0 because at the stationary point, the dy dx is equal to 0. Now we move on to solve for x. As we solve for x, in the dy dx, we are going to get the x, which is equal to -1/2. Now that we have obtained the x value, we now move on to find the y value. So it will be easy to find the y value simply because we are going to substitute the x value into the y. So wherever we have x, we substitute with a -1/2. So now simplifying that, we are going to get the y of 25/4. Therefore, the stationary point is -1/2 and 25/4. These are the coordinates, the x and the y coordinates. And this implies that we have a maximum point with those coordinates. So that's how we find the maximum point. Now, let's look at the second type of turning point. This is the minimum point. This is the second type of a point, minimum point. So we are saying that a minimum point occurs when the dy dx is equal to 0. And the dy dx should be less than 0 before the minimum point, and the dy dx should be greater than 0 after the minimum point. So this is the opposite of what we had for the maximum point. Therefore, in our case, from the graph that we have on the left-hand side, the point P is a minimum point. So the gradient on the minimum point is equal to 0. That's something we know. However, if we get a point that is the x-coordinate on the far left or before the minimum point, the gradient of that particular point should give us a negative, and after the minimum point, we should get a gradient that is positive, as displayed by that particular graph. Let's take a look at example 2. Find the coordinates of the stationary points on the curve y is equal to the square root of x plus 9/square root of x. The solution. We know that we can actually express y as x to the power half plus 9x to the power minus half. This is from the laws of indices. If you want to know more about indices, we have videos on indices, so make sure to check them out. Now, we find the derivative of y, dy dx, which becomes that. And then we equate that to 0 because at the stationary point, we know that the dy dx is equal to 0. When that happens, we move on to solve for x. So from the dy dx is equal to 0, we solve for the x. Solving for x, what I did there was simply multiplying by x to the power half. All the terms that simplified to x to the power 0 minus 9x to the power minus 1 is equal to 0. And of course, expressing this in other terms, I would have 9/x is equal to 1. Solving for x, x becomes 9. So now if x is equals to 9, I can substitute for that x into the y so that we get the y coordinate. So now that the x is 9, we substitute for that 9 in the y, so we're going to have root 9 plus 9 over root 9. And simplifying further, we are going to get y is equal to 6. Therefore, the stationary point is 9, 6. But for now, we have no idea what type of a stationary point this one is. So to determine the nature of the stationary point, we are going to use the sign change method. Right, so remember, our x-coordinate that we obtained was a 9. Therefore, we are going to get values that are before 9. For instance, a 4. If we substitute for a 4 into the dy dx or the y prime, because it's the same thing, so we are saying y prime of 4 would be that. And simplifying this one further, we are going to get a y prime of 4 being equal to 1 over 4 minus 9 over 16. And simplifying further, we are going to get the y prime of 4 being equal to minus 5 over 16. And we know that this value is less than 0. So that is before the point. Then we get another point that is after the point that we obtained, the x-coordinate of the point, which is the stationary point to be precise. So that we are going to let x be, for instance, a 16. So when we do that, we substitute for that x into the y prime of 16. We are going to get that, and simplifying further, we are going to get y prime of 16 being 1 over 8 minus 9 over 128. And of course, that would then become 7 over 128, which is greater than 0 because it's positive. Now, we have this, so the stationary point 9, 6 is a minimum point because this satisfies all the conditions of the minimum point. We have obtained the x-coordinate when dy dx was equated to 0. Then we got values that were before that x-coordinate. We obtained the sign of the dy dx, and we did the same thing after that particular point. So this is a minimum point. Let's move on to the final type of a turning point. So we have what we would refer as the point of inflection. So this is not really a turning point because it still maintains the gradient before and after. We still have the same gradient, though the dy dx is equal to 0 at that particular point. So this one is not necessarily a turning point per se. Now, a point of inflection occurs when 1, the dy dx is equal to 0, and either dy dx is greater than 0, then moves to dy dx is equal to 0, where we have that stationary point. Then from there, we get the dy dx being greater than 0 again. So it maintains the gradient before and after that particular stationary point. Or we can have it in this manner. The dy dx is less than 0, then moves to the dy dx is equal to 0, and then again goes back to the dy dx is less than 0 once again. Now we've got the graphs that display the situation at hand. So these are known as points of inflection. Right, so for instance, point B on the left-hand graph is a point of inflection. QB would have a gradient that is negative, and from BC we also have the gradient that is negative, but at point B the gradient is equal to 0. Now let's take a look at the final example. The equation of a curve is y is equal to x squared minus 9 over x squared. Find dy dx, and hence explain why the curve does not have a stationary point. Now, the solution. We know that we can actually express y in terms of 1 minus 9 over x squared. We covered such in the topics polynomial divisions. So make sure to check them out. We explain a lot of this concept in those videos. Moving on, we are going to have y expressed in this manner, 1 minus 9x to the power minus 2, so that it's easy to differentiate. When we differentiate that, dy dx becomes 18x to the power minus 3. With that, we equate it to 0 because we are looking for the stationary point. So equating that to 0, we are going to have that. And now trying to solve for x. Now we are going to have 18 over x cubed is equals to 0. Now trying to find values that satisfy that. Well, if you can see, you see, and you know what would happen. But anyway, let's play around with it. Expressing x cubed being equal to 18 over 0. So we know that any number divided by 0 becomes undefined. That is to say that we cannot find solutions of x. With that, it implies that y does not have a stationary point. So we have proved that. And that's how we answer the question. If you have made it thus far, I say congratulations. I'll leave you with the following task. A curve has equation y of x is equal to x cubed minus 6x squared minus 15x minus 7. Find the stationary points and determine their nature. Remember, your feedback, questions, and opinions are always welcome here. Make sure you post in your questions and we will see how best we can assist. Because at Numbers Simplified, we take pride in solving such questions. Thank you so much for watching Numbers Simplified. Make sure to subscribe, and God loves you.